Welcome back. We are looking at parametric equations, and then we're looking at calculus with those. And calculus, remember, is derivatives and integrals, and then thinking about integrals, we can use that for arc length and surface area and other fun stuff. So let's get to it. The big idea for parametric equations, parametric functions, parametrically defined functions, is that we are looking at two different functions. A function that is describing our motion in a horizontal or x direction, and a function that is describing our motion in a vertical direction or the y direction. Those are both continuous. Continuity gives us lots of things, namely derivatives and integrals that are nice. Well, we get integrals, and then continuity, it helps us with being able to take derivatives, but we still need differentiable functions if we're looking to take derivatives. Otherwise, we end up with cusps, and that's not going to give us continuous derivatives, but we'll talk about that a little bit later. But we have our function x and our function y that are depending on this other parameter, and it's a different variable. Generally, we call it t, and it helps us to think about that in terms of time. And this isn't something new. This is actually, we kind of talked about it when we were looking at related rates, because with related rates, we had all of our dimensions of our things that we were looking at in terms of time. We were looking at derivatives in terms of time. So thinking in that way might help us to really grasp what we're doing with our parametric equations. But when we're looking at parametric curves, that is going to be from this x and this y separate functions that are both depending on our parameter t. So a lot of people like to describe this as like, what's the motion of a bumblebee? Well, you can't really show like exactly, like there isn't necessarily a pattern. It's kind of like going wherever it wants to, in whatever direction it wants to, but describing that motion, just breaking that down into an x and a y coordinate, and then it helps you to be able to determine where that bumblebee is at any given time. So if thinking about bumblebees helps, then by all means think about bumblebees. But that is parametric curves. So we have x and y that are coming from these functions, and those are depending on t, which we like to think about in terms of time. So let's try to do this, sketch a parametric curve where we have this function for x and this function for y. So this set of parametric equations gives us our parametric curve where we have our coordinates x and y coming from these equations. So what should we do? Well, we should make a table. And making a table is generally a really helpful way of organizing our thoughts. So we have a t, an x, and a y column in our table. And should we just like plug in some values? I think so. Let's start with what, like -2 maybe? Because this looks kind of quadratic. -2 sounds good. So -2 squared is 4, minus 2 is 2, and -2 times 2 is -4, minus 1 is -5, and then I'll just chug through and plug in some more. So -1, maybe 0, maybe 1. So try those and see if we agree. Getting 0, -3, 0, -1, 2, and 1. So I'm getting some points. That's nice. So after we make the table and we plugged in our parameters, we've got to plot it. So let's plot some points. But we're looking at our x and our y coordinate. So we're not using t. But our time t's are going to give us our coordinates. So we have like 2, -5. It's poorly drawn scale. 2, -5. Down here, let's say. Then we have 0, -3, 0, -1, 1, 2. Alright. And does that help us? Maybe we need another point. Maybe we need to see where this vertex is going to be. Let's plug in like -1/2. So -1/2 squared is -1, or positive 1/4 plus -1/2 is positive, -1/4, and then -2, -1 minus 1 is -2, so we got -1/4 negative 2. So we get that. Something like this. And we actually started here, and we do get a direction, because as our t's are going up, our curve is going that way. So if it was a bumblebee, starting here at time negative 2, and then following that curve. Okay, so now we have successfully sketched the parametric curve for this set of parametric equations. So what if you didn't want to deal with like the picture? Like thinking about the picture is nice, and you could think about like, okay, so our x's are giving us something that's more of a parabola, and our y's are giving us something that's more linear, so we're going to end up with a parabola. Might be shifted a little bit or stretched or skewed, but we are getting a parabola. What if you didn't feel like doing that? Or what if you just needed to think about it analytically, not necessarily graphically? Well, we can eliminate the parameter from our parametric equations by choosing a t that we're going to solve for that t, and then plug it into the other equation. So now we can eliminate this t from our parametric equations, and we just have an equation in terms of x and y. Well, it's helpful to choose a t wisely. So think about which t we want to solve for. Do we want to solve for this t, or do we want to solve for this t? We definitely want to simplify our life. So we probably want to deal with the y's t. And then, that's a y, not a t. We need a t there. Minus 1 to solve for t. So we get t equals what? Y plus 1 all over 2. Yes. And so we plug this t in here wherever we see t's. And then we end up with x equals y plus 1 over 2 squared plus y plus 1 over 2. We can do some algebra, so we get y plus 1 quantity squared over 4 plus 2y plus 1 over 4. And so then we can simplify this more if we want to. So we get what? X equals y squared plus 2y plus 1 plus 2y, it's over again, plus 2 all over 4, and that's what? 1/4. I'm just going to pull that in front. We got y squared plus 4y plus 3. And so that is very clearly a parabola, and we see our stretches. This does factor, so that's nice, and we end up with those vertices that we were looking at, those y-intercepts that we were looking at. And then halfway between those y-intercepts is going to give us our vertex. So that's nice, but also helpful because we end up with just an equation that relates our x and our y, and we've eliminated our parameter t. All right. The next thing up is that cycloids are very cool. This is a cycloid, this blue shape, and that is from, if you imagine like a wheel or any sort of circle, but I would probably say you're thinking about like either a bike wheel or like a car tire. If you put like a dot on the edge of it, and then you spin that wheel around, like you roll it on the ground, then the cycloid is this shape that's coming out from following the path of that dot. If you were doing some sort of like, I don't know, like long exposure photo or something like that. So you have a wheel that's traveling and there's no discontinuity in where that tire is in relation to the ground. There's no like slipping or no, like spinning the tire where there's discontinuity there. And so this is very cool. And these sharp turns right here, this sharp turn, we don't have a differentiable function there, and that is also called a cusp. And that's where you have a sharp turn where it's not a smooth curve. So we have smooth all here, but then right there at that cusp, it is not smooth, where that point is hitting the ground, and then so on, right? So then, like this, as if we continue the cycloid, then we end up with this. But it's not a circle that's called a cycloid, so do some research on that. It would be pretty cool. So, promised you calculus. So here's where the calculus starts. If we have our plane curve defined by these two parametric equations that we have x and y, and let's also assume that our derivatives with respect to x and y, of x and y with respect to t, so this is dx dt, and this is dy dt, that those both exist. And we also assume that our derivative derivative of x with respect to t is non-zero. And that's important, which we'll see, I guess, like right here. That our derivative, dx dy, or dy dx, our derivative of y with respect to x, is given by our derivative of y with respect to t over our derivative of x with respect to t. And this, you can kind of see how that algebra works out, but we can also look at a proof very briefly for that. So, because like if you think about dy dt, this is change with respect to time, and then we're dividing by dx dt, that's an x, then that's dy dt times dt dx, right? And then those differentials with respect to differentials of t, those go away, and we end up with dy dx. But just think about this in terms of like a composition of functions. If we had our function, let's call it capital F, and that's our y value. So that we can also rewrite as our function of x with respect to t. So now if we take our derivative, then we end up with our derivative of this times x prime of t, right? Because of the chain rule. And so if we're looking at this all together, then we can also rearrange our sides so that we have our derivative dy dt divided by x prime of t, and that's equal to f prime of x of t, which is, that's our dy dx, and this x prime of t is going to be, dx dt as written there. So then we get dy dx is dy dt over dx dt. And there you go. So if we're asked to find the tangent line or lines to the parametric curve, that means that we need at 0, 4, and we're tangent to our parametric curve given by these two parametric equations. Then what do we need to do? Well, first we need to remember what tangent line means, right? That means that we have the same slope as the derivative, like our slope of our line is equal to our derivative at that point. And how do we take our derivative? Well, we just learned that, right? We need y prime is 2t, x prime, I guess with respect to t. Let's be responsible there. That's a t. I'm sorry. 5t to the 4th minus 12t squared. Okay. And so if we have that, then we can also find dy dx. And that's going to be our ratio of those. So we have 2t over 5t to the 4th minus 12t squared. And, well, when is this going to give us, what are we going to get from this? We have this in terms of t, but we also just kind of have, like, this is an expression, but it's with respect to t, so we need to think, what can we do with this such that such that we can still have the same coordinates that we're looking for. Because we're looking to deal with 0, 4. So x is 0, and 4 is y. So when is that going to happen? Well, we need to look at our original parametric equations to figure that out. So when is 0 equal to x? When 0 equals t to the 5th minus 4t cubed. This is secretly more algebra, so we get t cubed times t squared minus 4. That equals 0, and then that factors, right, because it's a difference of squares, so we end up with t cubed times t minus 2 times t plus 2. So t can be 0 or plus or minus 2, right? Okay, so those are some options for our t's. But we need also to have our y coordinate. Let me change colors real quick. We also need our y coordinate to equal 4. So we need 4 to equal t squared. And when does that happen? When t is plus or minus 2 or minus 2. So that eliminates 0 as an option. It's no longer a contender. But we do have plus or minus 2 as our options for what our t's can be. So we have that needs to go into here. Let's switch to galaxy something. So we have dy dx is equal to 2 times 2 over 5 times, and I'm going to factor this out, this 2 squared, I'm factoring like this because I'm responsible and I do math responsibly, times 2 squared minus 12. Okay, so then those go to 1 and we end up with reciprocal of 5 times 4 is 20 minus 12 is 8. So dy dx equals 1/8 for t equals 2. And then let's sneak on over. Let's try t equals negative 2. So then we have dy dx is 2 times negative 2 over negative 2 squared times 5 times negative 2 squared. Sneak this over. Minus 12. So then that cancels with that, but we get a negative 1 in our numerator, and so we got 1, or negative 1, sorry, 12 minus 8, nope, yeah, 8, negative 1/8 as dy dx right there. So if we're looking for our tangent lines for our final answer, we need to take our points and our slopes. So we have y minus 4 equals 1/8 times x minus 0, and y minus 4 equals negative 1/8 times x. And so we end up with actually 2 different tangent lines at the exact same point. And let me pull up a picture for this to make a little bit more sense. So the red curve is the parametric curve. We see that we have that 0 that we were looking at before, but that doesn't give us the same output of y is 4, so this is our only location that we're looking at, and we're looking at 2 different tangents. We got the blue and we got the green lines. And the little triangles indicate the direction of the parametric curve. As we plug in different t's that are increasing, our curve goes like that in this direction. And that's from Paul's online notes. Good old Paul's online notes. Alright, so look at this example and try to figure out when we have horizontal and vertical tangents given these parametric equations, this set of parametric equations that gives us a parametric curve. When are we having horizontal tangents? That's where our dy dx equals 0. And our vertical tangents when our dx dt is undefined. So try that out. So let's start with just dx dt is 3t squared minus 3. dy dt is 9t minus 0. 9t. Not a 9. 6t. Because of the power rule. My goodness. 6t. Alright. So, we're looking for horizontal and vertical tangents. Actually, the vertical tangents are slightly more straightforward. That's when our dx dt is undefined, or is 0, so that dy dx is going to be dy dt over 0, so that's undefined, and that gives us a vertical tangent. So just set that equal to 0, and what t's does that happen for? That's a 3. So we move that 3 over, divide by 3, so we get a 1 equals t squared, so t is plus or minus 1. So that will give us some t's with vertical tangents. And how do we figure out where those locations are? Well, we need to plug those in to x and y. So we have x and y are going to be, x is negative, positive 1 minus 3 is going to be negative 2 when t equals 1, and then t is negative 1. Maybe I should just do this in a table, huh? So let's see what happens if I have, just follow my own advice, my goodness. Okay, so we have t is positive 1, that means that x is 1 minus 3 and negative 2, and y is 3 minus 9, which is negative 6. And then when t is negative 1, because we have the other negative 1 down there, negative 1 cubed is negative 1, plus 3 is positive 2, and then negative 1 squared is positive 1 times 3 is 3 minus 9 is negative 6. So we have vertical tangents at the points negative 2, negative 6, and 2, negative 6. That symmetry is really nice. I like that a lot. Okay. So that's our vertical tangents. What about horizontal tangents? When do we have horizontal tangents? That's when dy dx equals 0. And so that's when dy dt over dx dt equals 0. And that's really whenever dy dt is going to be 0, right? So that's going to be when 0 equals 6t over, I guess, 3t squared minus 3. But, I mean, this is going to be when t equals 0. And so, when does t equal 0? What happens, or where does t equal 0? At 0, negative 9. So we have a vertical tangent, or a horizontal tangent. At 0, negative 9. Boom. When we're taking our second derivative, remember second derivative is like giving us a number for the concavity and stuff like that. Positive is concave up, negative is concave down. Our second derivative for our parametric equations is not going to be the second derivative of, like, it's not y double prime with respect to t over x double prime with respect to t. This is not what that is. That's not the same. So what we are really doing is that we're taking our derivative with respect to x again. So we are looking at dy dx, which was, as we recall, dy dt over dx dt. And we're taking our derivative with respect to x again. But what's really happening is that we are taking this by dividing by our derivative with respect to x and differentiating our y dx with respect to t again, because we are trying to differentiate with respect to t as our second derivative. So we're taking our derivative with respect to t because that's our parameter, that's what we're putting into our function, and so in order to differentiate, we need to take our derivative with respect to that original parameter t again on our first derivative. So what's really going to be happening is that you're going to calculate, in order to figure out what our second derivative is of our parametric curve, our plane curve, is plane, P-L-A-N-E, plane curve, is going to be looking at our first derivative and then differentiating that with respect to t, and then dividing by our first derivative of x with respect to t. So that's what's happening down here. And then you can analyze this in the same way that we did before when we were thinking about curve sketching, where you have your second derivative is telling you about the concavity of your equation or your function. So more calculus, we can look at area as well, because if we can take derivatives, we can take integrals, right? If we have our area under our parametric curve, then we can write it, as long as we have non-intersecting plane curve, like we don't have, something looking like that, which we did in the previous problem. But if we're looking at only like one part of this instead, we start it at a particular parameter t where we don't get an overlap. Well, maybe we should start there instead for our t. Our t would start at this time and then go to like maybe this time or something like that. So we have bounds, and those are on our t, our parameter. And our input for our integrand is going to also be in terms of t's. So all of our operations we're dealing with are in terms of t. Our area under the curve is going to be our y with respect to t times our derivative of x with respect to t, and we're integrating with respect to time. And the reason this is coming about is because when we're looking at the chain rule and undoing the chain rule, then this is a necessary element of that. And our parameters are, again, with respect to time. So our t, our parameter. So our bounds and everything in our integrand and what we're integrating with respect to are all in terms of the exact same thing. They're all with respect to our parameter. So what we're dealing with here should only be in terms of t's. And if you don't have your integrand only in terms of t's, then you need to do some more substitutions so that you can actually integrate the thing that you're looking to integrate. So let's try it. So all of a sudden, we have a parameter that is no longer t, it's theta. And that is okay. We can change what our parameter is as long as, we're responsible about how we deal with it. So we do have our bounds on our theta. We have x in terms of theta, and we need our derivative of x with respect to theta. Let me zoom in a little bit. Okay. And that's going to be 6 times 1 minus cosine theta. And so our area is going to be from 0 to 2 pi of 6 times 1 minus cosine theta times 6 times 1 minus cosine theta d theta. And parentheses there. Alright, that's not so bad. I guess we have the exact same thing, so we can just multiply through a little bit. So we get integral from 0 to 2 pi of 36 times 1 minus 2 cosine theta plus cosine squared theta d theta. This seems like it should be nice. What's nice about this? Well, this cosine squared, the cosine squared we can do something with, huh? So this cosine squared theta, is there any way we could rewrite that? Well, we know that cosine of 2 theta is cosine theta squared minus sine squared theta. And so that means that along with our Pythagorean identity of sine squared plus cosine squared, that equals 1, can I rewrite this sine squared in terms of 1 minus cosine squared? Absolutely. So we have cosine of 2 theta equals cosine squared theta minus, and then 1 minus cosine squared theta from this Pythagorean identity, which I'm going to erase now, because you have that in your brain, right? So then we have cosine of 2 theta is going to be 2 cosine squared thetas minus 1. And can I get cosine by itself? Yeah, if we have cosine 2 theta plus 1, or cosine squared by itself, divided by 2, that equals cosine squared theta. And that's what we have right there, so we can substitute that. Because that gives us a lovely power reduction, and then we don't have to deal with power of cosine, which is nice. We'll just pull the 36 out. So then we have 1 minus 2 cosine theta plus cosine 2 theta plus 1 all over 2 with respect to theta. I guess we can, oh, that is over there. So then we end up with 36 times our integrand from 0 to 2 pi. We got this 1 and this 1/2 that we're going to combine to 3/2 just to make the algebra a little cleaner, minus 2 cosine theta plus 1/2 cosine 2 theta d theta. Integrate that, and what do we get? We get 3/2. Oh, sorry, we have the 36. We don't forget about that. 3/2 theta minus, plus, no, minus 2 sine thetas plus 1/2 sine 2 theta. Then we got to divide by 2 again. So we have this multiplied by 1/4. We're going from 0 to 2 pi. And you plug that in, and what do you end up with? You end up with 36 times 3 pi minus 0 plus 0 minus parentheses zeros. And so we end up with, what is that, like 90 pi plus 18 pi, 108 pies as our area under our curve for, where'd it go? This parametric curve given these parametric equations. Whew. We can also look at arc length, which is really nice, and it also breaks down really nicely. Remember when we were doing arc length initially, and we were thinking about the Pythagorean theorem, but we had to do a little bit of, I don't know, creative algebra in order to get our Pythagorean theorem to give us something that we could integrate nicely. Well, this is actually like much nicer because we're separating our x and our y, and so it's a lot clearer, I think, that you can see that this comes from the Pythagorean theorem because you're looking at your small change in your x direction, your horizontal direction, squaring that with, and then adding that with the small change in your y direction, your vertical direction, squaring that, and then taking the square root of that sum. I think that that's a lot more clear that it is from the Pythagorean theorem instead of all this like 1 plus business. So that's really nice. I think that's pretty cool. You can also think about our familiar arc length formula in terms of this, because whatever you're taking your derivative with respect to t, that becomes a 1, it's gonna be like, that's like your parameter. I don't know. I think that helps. But if it doesn't help you, then just forget that I said that. But if that helps, cling to that. That'll be good. But this is very nice Pythagorean theorem, and so we're going to use the arc length formula for this set of parametric equations, and we also have bounds, and these are all in terms of t, so that's really nice. So try that out. We'll see how we do. So looking at these, this is actually going to turn out really nicely because we have 3t inside both of our functions. So that's really nice. And we're also multiplying by 3 on both of them, which is also very nice. Why is that nice? Well, we're going to end up with a lovely, lovely, lovely Pythagorean identity. So we're looking for the arc length, which we typically call s for some reason, going from 0 to 2 pi. We're looking at the square root of our derivative of x with respect to t, so that's what, 9 times cosine 3t, and then we are taking this and squaring it, plus our derivative of y with respect to t, which is going to be negative 9 times sine of 3t, and we're squaring all of that. And we're looking at this in terms of t. So, we're going to rewrite this a little bit. We get 81 cosine squared 3t plus negative 9 squared is going to be 81 again, and we're happy. Do you see why we're happy? Because we get 81 that we can factor out, and then we just get a Pythagorean identity, which is amazing. And so this is super easy to integrate now, because this is going to be 1. Well, 81 times 1. But then the square root of that. So this whole thing is going to be equal to 81. And so we end up with our integral from 0 to 2 pi of 9, which is so easy to integrate. We have 9t from 0 to 2 pi. And that's what? 18 pi minus 0 pi's, which is 18 pi. That's our arc length for that. Amazing. Math is so cool. Alright, last up, we have our surface area, which is just taking our arc length and rotating it, right? So, our surface area that we have for a parametrically defined curve, this one right there, we can take our surface area for that surface of revolution, where we're looking at our arc length and we're multiplying it by our radius, which is our y, as long as we're rotating about our x-axis, right? If we're rotating about our y-axis, then this would switch to x. And then we have a 2 pi, because 2 pi r h is that's what we're dealing with, right? We're looking at 2 pi r h to find our areas of our rectangles that are on the outside of our cylinders. So our surface area for this parametric curve about the x-axis, which is nice because then we can use this formula exactly. We didn't have to change this to x of t, which we would if this was in terms of the rotating about our vertical axis, our y-axis. But we don't have to do that, which is nice. So let's do this. We end up with our surface area, which we also call s, that's curious, is 2 pi times our integral from 0 to pi halves of sine cubed theta times root, what is this? X prime is 3 cosine squared theta times sine theta with a negative out front, and y prime is 3 sine squared theta times cosine theta because of the chain rule. So we end up with negative 3 cosine squared theta sine theta, all of that squared, plus 3 sine squared theta cosine theta squared, and then I ran out of space for my d theta. There we go. Okay. And can this get nicer? I certainly hope so. So what do we get? 2 pi from 0 to pi over 2 times sine cubed theta times root, what is this? 9 cosine to the 4th theta sine squared theta plus 9 out of 3. 3 squared is 9 sine to the fourth cosine squared d theta. Okay, okay. So we can factor out a sine and a cosine, or sine squared and cosine squared for anything in our integrand, inside our radical in our integrand. So we get 0 to pi over 2 of sine cubed theta times, we can pull out that 3 as well. So we have 3 sine and then sine theta cosine theta times this root cosine squared plus sine squared, I forgot my theta there, d theta, and that's going to go to 1. So now we have 2 pi times our integral from 0 to pi over 2 of, oh, and I'm going to pull the 6 out front because we have 2 times 3, and this is sine to the fourth times theta times cosine theta d theta. Integrals of this trig function, well, that's actually not so bad because we can just use a straight u because we only have one cosine to deal with, so that's nice. And so let's substitute where u is going to be sine theta. And so what do we end up with? We end up with u to the fourth, and the signs are fine. So we end up with our integral of u to the fourth, which is u to the fifth over 5. So sine 5 theta over 5 from 0 to pi halves. And this is all times 6 pi. And what is that? We get sine to the fifth of pi, sine of pi over 2, which is 1, times 1 over 5 minus 0. So we end up with 6 pi over 5 as our surface area. 6 pi over 5. Let me check that to make sure that's right. Whew, yes, it was correct. This is also from Paul's online notes. All right, cool. That just about does it. Sorry for the dead time at the end. But think bumblebees. That's like the purpose of parametric curves, being able to describe the motion of bumblebees. And then everything that we did in calculus so far, we can do with parametrically defined curves. We just need to be careful to take care of our variables well. And don't forget the chain rule. Cycloids are cool, so please do look them up. And the algebra involved here is just algebra. It's just algebra. You can do it. But yeah, parametrically defined equations, they work with calculus, which is quite lovely. All right, see ya.